Good evening, one and all present here. Welcome to today's Kaapi with Curiosity talk. To officially welcome you all, I call upon our director, Dr. Guru Prasad.
Respected Professor Spenta Wadia, Madam Wadia, Professor Sam and Mrs. Sam, and ladies and gentlemen, my colleagues from JNP, I welcome you all to the yet another lecture under Kaapi with Curiosity. You all know that this is jointly organized by ICTS as well as JNP, and it is being held here. And today, on a very interesting topic, Professor Spenta R. Wadia has kindly agreed to come and deliver this talk. A person of his eminence has come here, and he's the founder director of ICTS of TIFR. So thank you very much on behalf of ICTS as well as JNP especially. And let me say only one sentence. Whenever I see the topic, a history of time, lay people like me, nevertheless enthusiasts like me of physics, remember Stephen Hawking's A Brief History of Time. I'm sure that Professor Wadia is going to deliver a talk which will be a history of time which is very elaborate. Thank you, sir. Thank you very much. Welcome to all of you once again. Thank you, sir. Now I request Professor Sam to introduce the speaker formally. Thank you, sir.
Nimelargu Hardika Swagata. Hearty welcome to all of you. And today's speaker is Professor Spenta Wadia, and you're going to hear about a history of time. We have a few minutes, whatever minutes are, in order to talk about the institute which he has been instrumental in building before I talk about him. So the ICTS is located in Hesargata, and we have a three-pronged approach at ICTS to science. One is to take science to the public, and this forum is an example of that. And that is the outreach wing of the ICTS. Apart from that, we have scientific research at an international level in several areas of physics, mathematics, computer science. And also, there is the conferences. We organize conferences at ICTS on subjects which are at the forefront and the cutting edge of science these days. So this institute was conceived of and essentially built by Professor Wadia. And let me come now to Spenta himself. I can only describe him as a force of nature. Studying nature is a full-time activity, but studying a force of nature is something else. So he's been instrumental in building up the string theory group in TIFR, which is one of the world's best groups in this area. And apart from that, he's also conceived of the ICTS and executed its construction. And you can see the results of it on these two slides. And let me also say that apart from science, Spenta has also got an artistic temperament. And you can see that best in the logo, which is up just next to the letters ICTS. That logo combines science and art in a very holistic way. And that probably describes Spenta better than any more detailed description I can give you. So without further ado and without wasting more time, whatever that is, I ask Spenta to give us his talk.
Okay. Good afternoon, everybody, and thank you for being here on a Sunday afternoon. Thank you, Dr. Guru Prasad, and thank you, Sam, for your introduction. I must say that I take no credit for this logo. This logo is due to Bhaskara II, the great Indian mathematician who lived in Karnataka many centuries ago. It's a visual proof of the so-called right-angle triangle theorem, which I purposely don't want to say is Pythagoras' theorem, because Pythagoras perhaps had nothing to do with it. Okay, so let me start my talk. It's about a history of time, and clearly it brings out memories of Stephen Hawking's very beautiful book. brief history of time and an even briefer history of time, which he wrote much later. But this is a little different, actually. I mean, so this is really a bit different about the idea of time, actually, since antiquity till modern times. Okay, so so let me just first begin with time and celestial phenomena. So our awareness of day and night is obvious as the sun appears and disappears daily. This is related to the spinning of the earth on its axis, an explanation that of course came much later. Day and night are wired into our genes also. So there is, for example, the secretion of melatonin in the evening that induces sleep. Such circadian rhythms are present in animals, plants, and other living matter also. So just imagine yourself about 10, 15, 20,000 years ago, our species, you know, how they perceived. I just wanted to create a certain understanding of how our species, that is humanity, came to understand time, the passage of time, and also the measurement of time. And this is one of the important things I will want to talk about in this talk. Okay, so so the awareness of the duration of a year, for example, now we go from day to a year, during the early history of our species is through the seasons and their manifestation in terms of hot and cold weather, as we can experience all the time. The appearance of fruits and flowers, you know, fall, etc. Migratory patterns of birds, animals, and when agriculture came about, a time of sowing seeds and a time for harvest. And this whole issue of seasons is very simply explained in terms of this very elementary diagram. And here is one of the important things about planet Earth, that it has a tilt of 23.4 degrees, I think, with the plane of its orbit around the sun. Is a very fundamental number of our planet, without which most of us, I mean, maybe some sort of life may not have been possible of the type we have today, actually, because this tilt is very important. Okay, I don't want to get into all those extraordinary events of nature which has us all sitting here, but this is one of them. Okay, so the whole idea basically is that you are looking at some sort of a periodic motion in order to understand the notion of time. I mean, originally, so the other periodic motion which our ancestors observed in the sky is the waxing and waning phases of the moon, right? And the rise and ebb of tides due to its synchronous rotation about its axis and its orbit around the Earth. You see the rotation of the moon actually coincides with its rotation around the Earth. So this synchronous rotation is there. And that, for many centuries actually, since antiquity, became a natural timekeeper. So for example, a lunar month became a natural unit measuring time difference between different phases of the moon, which are sort of depicted here. So early in history, it was our sensory perception of the motion of the Earth in the solar system and the visible periodicity of the phases of the moon that implied a passage of time. So the notion of time, in summary, grew out of the almost periodic cycles of the natural world. Now, this word almost is very, very important actually, because there is no real periodic cycle. Okay. And that fact has continued into the modern world. You look for periodicity, which are robust, stable, and in a deep sense, that's the theme of this talk. Okay, so let's go on. By the way, Disha, how much time do I have? Okay. All right, I have a notorious reputation. All right, please. Okay, thank you. Okay. Okay, so more sophisticated timekeeping devices emerged based on astronomy. Okay. One imperative came from navigation at sea. As the seasons change, the movement of the constellations, a group of stars, is visible in the night sky, and this is due to the orbit of the Earth around the sun. See constellations. So I'll be quoting a lot from this very beautiful book by James Vincent, Beyond Measure, The Hidden History of Measurement. So here is a quote. The synchronization of celestial and terrestrial changes naturally suggest a causal relationship between them. So observing the motion of constellations and the planets became a way of explaining and predicting events on Earth. It's a very important point, actually. You see, I mean, this talk is a little bit also about history and sociology. This is what I'm interested in. The physics part I know, actually, but in preparing this talk, I have learned a few things about the history, sociology. So the synchronization of celestial and terrestrial changes suggest a causal relationship between them and things that happen on Earth. Okay, so that rings a bell, right? However, celestial timekeeping has inaccuracies built into it because celestial motions are never perfectly periodic, as I mentioned to you. For example, the length of the year measured between equinoxes, when the sun is, when you have equal days and night, is 365.2422, which over centuries, for example, over 5 centuries, can grow into a difference of 0.24, etc. times 500, which is 121 days. It's quite amazing. Similarly, the average length of a lunar month is 29 days, 12 hours, 44 minutes, and 2.8 seconds. All this is from internet resources, actually, so, and some books. So now comes the very big point of the fact that instead of just looking at the sky and the celestial objects to understand the passage of time and its measurement, societies since the 3rd millennium, for example, the Sumerian civilization, developed various terrestrial timekeeping devices. For example, the water clock, the sundial, sand glass, incense, burning of incense, and a candle clock. So I've sort of indicated them here. This is the water clock, actually. It's very, very ancient. And basically what it does is that, you fill it up with water and, depending upon the dimension of the faucet, etc., you can make a measurement of time. And this is very, very ancient. Then there is the instrument in which the water has been replaced by sand, which came a bit later. And then there is this Chinese incense clock. The time is measured by means of powdered incense burnt along a pre-measured path. And then there is a sundial. This is the picture of an Egyptian sundial, which of course the Roman emperors also used later on huge columns. And I also thought I should mention about, I think perhaps one of the most accurate and complex sundials, which is at the Jantar Mantar in Jaipur. It's quite an amazing thing. I've seen it a couple of years ago, and it's worth a visit, actually. So these diverse devices are not very accurate timekeepers. For example, water clocks measure of time depends on the temperature of water, clearly. The sundial does not work at night or on a cloudy day. So the Chinese invented a candle clock, actually, the burning of a candle, which will also be can be used at night. So this is going on for the past, since the 3rd millennium, how to sort of measure time. And in each of these little things, you will see that the laws of physics are at play. You can figure it out for yourself, which laws are at play. Each of these things. All right. So now comes a very, very important thing. Perhaps this is the game changer in our history. So the oscillator escapement mechanism, which I have just drawn here, that creates the regular periodic beat of timekeeping, was originally developed in countries like China and the Middle East. Towards the end of the 13th century, European craftsmen refined this mechanism to create the first mechanical escapement mechanism clock that led to the mechanical clock. And here I have given two examples of clocks which I have myself seen. This one I have seen many years ago in the town of Rouen in France. And this is from my old city. I'm now a Bangalorean, but I used to be a Mumbaiker most of my life. And this is the clock tower at Crawford Market. And it functioned from 1869 to 1990. And now, of course, in 2017, they have restored it, but not as a mechanical clock, but it's powered by electricity, all right, by batteries. So, yeah, so this is the mechanical clock, the beginnings of the mechanical clock. And then, as time went on, the pendulum clock design was conceived by Galileo Galilei. There was a drawing also of a great Italian artist, engineer, Leonardo da Vinci. But I have not mentioned those details. But then Galileo realized that the swinging of some lamps in a cathedral, that the period of the swing is independent of the mass of the bulb. So it's an amazing observation. So then the working model, you see, ideas are one thing, but ideas to engineering to product is another thing. And that was done by Christian Huygens and constructed by Coster in 1656. Okay, so the mechanical clock continued to become more accurate with new innovations and reached its pinnacle in the 18th century. Okay. So now I want to tell you something which is new, Disha. This is not in the previous talks. This is about the marine chronometer of John Harrison. So which is the precursor of all our pocket watches, all our wristwatches, mechanical wristwatches, which I wear. So in 1770, after many trials and versions, since 1735, John Harrison, an English carpenter, made one of the most accurate and robust mechanical timekeeping devices that enabled accurate navigation on the high seas. I'll just read it out for you for accuracy, and then I'll try to explain a few things. So this clock was resistant to variations of temperature, humidity, and the rocky motion on high seas, and kept time to within 0.33 seconds of a day, more accurate than today's quartz watches, the quartz watches which you are wearing. So what was the big challenge? The big challenge in the timekeeping had to do with how robust the instrument is. You take a pendulum clock and put it on a ship, it won't be able to serve you well because of the jostling. Also, humidity, temperature. You see, the temperature will change there'll be expansion of the bob. So Harrison, actually, this same person, fixed that problem by putting two pieces of metal together, which would compensate for the expansion of one and the other. So the main challenge in clockmaking and timekeeping, even today, is about its robustness to temperature, humidity, gravity. How would you have a clock on the satellite? You cannot, because there's no gravity there. The standard clock won't work. So we'll come to that. So why was Harrison's contribution so important? So now the main problem in navigation was to know the longitude, where you are. Now latitude is not very difficult to figure out because of the tilt of the Earth again. But longitude was not easy to do. And this was a challenge, a question that was put to people like Newton, Galileo, others, and all of them felt it was a very hard problem to solve. And the reason is that you need to have a measure of time, which is a clock, which will survive being put on a ship and taken for a voyage. So suppose you have made such a clock, which Harrison did, then you have the same clock in Greenwich, for example, or some other city, and you carry another piece with you. So when you are at noon, for example, on your ship, you know the time of day, but you also know the time of day in Greenwich. So you then know exactly how much you have traveled. And if the clock is not accurate enough, the measure of the longitude is in great error. And this had actually led to a lot of navigation disasters, for which the London Longitude Society, I think that's the name, had put forth a prize of £20,000 in the 18th century, actually, to make this clock. So Harrison did this. Now the surprising thing is that I found out all this trying to prepare this talk, because one of my colleagues told me, have you read this book, Longitude? And I was a bit feeling strange that, we all the time talk about, all the scientists that make to the newspapers, but there are all these engineers actually whose contribution is so significant, so fundamental, that it's important for us to recognize it, actually. I'm very happy that I could learn about this and tell it to you. Okay, so since the Earth rotates 15 degrees per hour, okay, 360 degrees by 24, longitude is determined accurately by comparing local time, which I mentioned to you, with the time at a fixed reference point, for example, Greenwich Mean Time. This accuracy led to safer navigation, ultimately transformed maritime travel. Harrison's clock remains one of the greatest achievements in horology and set the foundation of modern chronometers used in precision time keeping. And this is very well documented in this very beautiful book by Dava Sobel. Just wanted to give you a snapshot of this. This is the last chronometer he made. He made several of them over many decades. H1, H2, H3, H4, H5. And these are the photos of the last one, the H5 chronometer, which I was talking about, which was successful. This is from here that, and of course, I'm not going to tell you the details of the engineering, but it is all available for you to read on the internet. And it's fascinating stuff, how this stuff works actually. To keep a time which is accurate to 0.33 seconds per day, you can only lose 1/3 of a second a day, and that's amazing actually, done in the 18th century. Okay, before I say this, I searched quite a bit about measuring time instruments in ancient India, you see, and I could only find one thing which is not very different from the Egyptian agora I showed you, that you take a vessel, put a hole in it, fill it with water, and see how long it takes to empty out as a measure of the passage of time. But I didn't find anything about craftsmen, engineering, about instrument making at all. This is bothersome, and I think we need to be cognizant of this and try to do something. It has lots of implications, which I understood immediately. Okay. Now, what is the social impact of the mechanical clock? So these are quotes from this very beautiful book. The mechanical clock propelled a new conception of time into the public consciousness, transforming it from a constant flow embodied in steady emissions of water, sand, and mercury to a quantified count, divisible, discrete, and measurable. As with monastic bells, public clocks organize citizens into a cohesive unit, turning what had previously been private lives into communal tides that rose, worked, and retired as one. The clock is not merely a means of keeping track of the hours, but of synchronizing the lives of men. I think should not say men, human beings, but anyway. So this is a social impact of the mechanical clock. And it basically is the beginning of the growth of the scientific method. The clock, which is a machine, became a symbol of a new way of conceiving the universe. That is mechanical philosophy. So let me read out. The mechanical philosophers reasoned that if clockwork was able to capture the movement of the stars and bring an elaborate automata to life, who was to say that the natural world did not operate under a similar logic? If nature worked like a machine, then it must rely on observable cause and effect. So Galileo Galilei, more than any of his contemporaries, crystallized the integration of experiment and theory and laid the foundations of the scientific method. He died in 1642, the year his intellectual successor, Isaac Newton, was born. So this finishes the first part of my talk. How am I doing for time? I'm halfway. Okay, so I'll speed up. Oh, wow. Okay. All right. So now I'll be talking a little bit about physics, actually, and stuff like that. Also, this is part of the history of physics. So Newtonian framework of physics, universal time, and the law of universal gravitation. And please bear with me, because there is a reason why the law of universal gravitation is important for us to understand how the GPS works. I'll come to that. So Isaac Newton establishes a framework of mechanics as all natural processes take place in space and time. This is a very simple simplification of what Newton did, because the language of Newton was not this language. It was in the language of Euclidean geometry and stuff like that, but that's too difficult to explain, understand. So I'm just using this. So Newton formulated the laws of motion in terms of the flow of time. This idea of flow of time is there. Those instruments were there, of the position of a point particle in a three-dimensional geometry. Okay, so you draw these axes, there's a curve here. This curve is parameterized by this stuff called time. It's a pretty abstract stuff here, actually. And so this is a curve, and the velocity and acceleration are given by time derivatives of the curve. I mean, that's the calculus he invented to understand these concepts. So geometry, calculus, and mechanics provide a description of motion. And the important point which I want to make is that time is absolute and the same for all observers. Okay, so coordinates of space can be rotated, translated, but time is the same. All our synchronization anywhere, whichever way we are moving, is the same in Newton's mechanics, actually. So it's absolute. And the laws of motion are these, the famous F equal to ma, and it's the foundation of all of classical physics. Absolutely, it is the foundation of all of classical physics. And next is he did more. I mean, of course, he did the law of universal gravitation, which we all know about gravity being always attractive by this law. And the important point is that it acts instantaneously, means if you have two objects, mass m1 and mass m2, and if this moves, this will instantaneously move. So this instantaneous interaction, as you see, will be the root cause of a lot of problems in physics, which will eventually be resolved by special general relativity, as we'll see. So it's always attractive. Okay, this is just a description of this equation. And Xavier. Okay, so this is a very important experimental fact. It's usually demonstrated by the Leaning Tower of Pisa, but I think Galileo reasoned theoretically to arrive at this. But that history I don't want to go into. And in the simple case of two bodies, this equation and the Newton's laws leads to the famous elliptical orbits of planets described by Kepler when the coordinate system is centered at the sun. So he took all this data of Tycho Brahe. It's an amazing thing. It took Kepler approximately 22 years from that data to arrive at the elliptical orbits. So that's the thing about gravitation. And now I just thought it is important to tell you that Newton's law does not explain gravity, but says that it works. And Newton was already aware of this in the 17th century. So I'll just read it out. This is a quote from the Principia, that one body may act upon another at a distance through a vacuum without mediation of anything else, by and through which their action and force may be conveyed from one another. See how difficult this English is to me so great an absurdity that I believe no man who has in philosophic matters a competent faculty of thinking could ever fall into it. Quite amazing, right? That he knew the problem with his law. And he says in 1713 that I have not yet been able to discover the cause of these properties of gravity from phenomena, and I feign no hypothesis. It is enough that gravity does really exist and acts according to the laws I have explained, and that it abundantly serves to account for all the motions of celestial bodies. So this is something so true to the scientific method that, I don't understand it, but these laws, agree with observations. Actually, the predictions agree with observation. And there it is. Newton knew the problem with his laws, actually. So this is very important, I think. More than many people who came after him. All right. Next chapter. So this is another very important chapter. So we saw the universal law of gravitation, the fact that it's an instantaneous interaction, but it explains a good part of celestial physics. And so it must be right in some approximation. I'll come to that now. Okay, so this slide is about, each of these slides actually can be a lecture course, some sort of a master's class or something. Each of them is so pregnant with so many ideas that encapsulated in one slide, because she's giving me only an hour. Okay, so there is this whole unification of optics, electricity magnetism, and electricity magnetism. And so the person who, in a sense, first understood that light has something to do with electricity and magnetism, I think, was Michael Faraday, experimentally, actually. He put a magnet in front of a beam of light and noticed polarization. This was amazing, actually. I always wondered, actually, how Maxwell somehow thought that his equations would lead to optics or identify it with light. This was one of the important inputs, I think. I don't know how Maxwell thought, obviously, but I thought this might be important to state. Then Maxwell unified electricity and magnetism and predicted the existence of electromagnetic waves and identified light as an electromagnetic wave oscillating electric and magnetic fields, as shown in this simple diagram. And the speed that he sort of almost correctly calculated was 10 to the 5 kilometers per second. The important point, what is the important point here? That the force between charged particles is not instantaneous in Maxwell's theory, unlike in Newton's theory of gravitation. And this force is transmitted by the electromagnetic field at the speed of light, which is finite. So the The two main important things about this slide is that there is the notion of the speed of light. The speed of light is finite, it's not infinite. It's very, very fast, but it's not infinite. And that it all comes from Maxwell's equation, which, as understood by Lorentz, that it has a certain symmetry, which led to, before that, led to, I always want to say that all these theories need experimental confirmation, solid experimental confirmation. So here is the experimental confirmation of Maxwell's prediction of electromagnetic waves. And this is Rangan's serendipitous discovery of X-rays. So Maxwell's theory is correct. So whatever else it predicts is also correct. I think that is the next slide. The implications of Maxwell's theory. That the speed of light is the same whether you run towards it or run away from it. Quite amazing. It's so counterintuitive, but this is the truth, because this is what Maxwell's equations tell you. So I just have a very simple thing I took from the internet about explaining this idea of time dilation, actually, which is forced upon you by Maxwell's theory. So now suppose you have an astronaut moving at a certain speed v, velocity v in this direction with respect to an Earth observer. So she's just standing on Earth and there is an astronaut that's just moving by. Okay. The speed of that astronaut is v. That astronaut has a timing apparatus. You know, there's a laser and there's a mirror. So the beam of light goes here and it's reflected back and so on. So, blip, 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 blip. That's the timer. So the astronaut times delta t. But for this observer, because the speed of light is finite, okay, light travels farther. It travels this distance, then this distance for the astronaut. Okay, and then you can, it's very easy, very beautifully easy that you can just look at this right angle triangle over here. This is the hypotenuse. This is one side and this is the other side. Then you can use the right angle triangle theorem, very elementary, to arrive at this very famous formula, which tells you that if delta t is the time interval observed by the astronaut, then delta t prime is the time interval observed by her, and it's modulated by a certain parameter, which is 1 upon square root of 1 minus v square upon c square. So if v is very small compared to the speed of light, you get simultaneity. That's what we are all used to. But if v is very close to the speed of light, then delta t becomes stretched very long. Okay, so this is a very simple but beautiful implication of the finiteness of speed of light. And this has been also experimentally observed. For example, in elementary particle physics, if you look at the collisions of elementary particles which produce pions, those pions are produced at relativistic speeds very fast. So if you are sitting in the frame of the pion decays very quickly, approximately 10 to the minus 29 or something. Strong interactions time scale. But for the experimentalist, who is like the Earth observer, the lifetime stretches, and that's why you could measure it. And this experiment of special relativity was proposed by Homi Bhabha, and that was one of the very good tests of special relativity. Okay. All right, let me move on now. This is about. So now let me come to something more, a little bit more sophisticated. So this Hermann Minkowski was one of the teachers of Einstein, and he took the theory of special relativity, which I have not explained very well or anything, and gave it a geometrical interpretation. So he said that time is the fourth component of a four-dimensional space-time. Now, we all recall from Euclid's geometry that the distance between 2 points is given by this simple formula, right? It's sort of rotationally invariant distance formula in Euclidean geometry. So Hermann Minkowski just put a minus sign here and declared that this is the sort of geometry which comes out of special relativity. So there is a geometrization of space-time that was introduced by Hermann Minkowski. And I think this played a very important role in setting up the general theory of relativity. So now let me explain the general theory a little bit, because we are getting to the issue of time slowly. Okay, right? So, so given that the speed of light is the same for observers in relative motion, as we discussed, there can be no action at a distance which is simultaneous for all inertial observers in relative motion, obviously. So there must be some problem with Newton's law of gravitation, because speed of light is finite. Every interaction, every sort of perturbation of one mass does not instantaneously inform the other one. So there must be something rippling and informing it. So that was the question. So immediately, I mean, Einstein concluded approximately in 1905 that there's a problem here. And so from 1905 to approximately 1915, November of 1915, when he gave the 3 lectures at Berlin Academy, Einstein completed the general theory of relativity, which is a theory of gravity in which the force of gravity is not instantaneous. It is communicated at a finite speed c, the same speed c, by changes in the geometry of space-time. So I have a little figure afterwards to explain that. So here the role of the electromagnetic field is played by waves of the metric of space-time. Those waves were observed in 2015 as gravitational waves. It's very interesting, approximately 100 years after their prediction by Einstein. Okay, so this is all these animations in my talk are all due to my friend Juan Maldacena, actually, who always lets me use all his animations for my talks, actually. So, so general relativity describes the changes of the geometry of space-time caused by massive objects to which other objects respond. So matter tells space-time how to curve, and curved space-time tells matter how to move. So space-time is like an elastic grid. It's communicative and it's causal. Each word is very important here, but very, very, very stiff. The stiffness is like 10 to the power 20 times stiffer than stainless steel. This is the reason why all of our motions does not produce gravitational waves, even though the motions of electrons are producing electromagnetic waves. And, it took a cataclysmic collision of 2 black holes to produce these gravitational waves, which were observed in 2015. And just to illustrate again the point I was making is that imagine this grid, very, very, very strong grid, and a very big, massive object like the sun over here, or even maybe the Earth. And if you look at this, I'm sorry, I think I did it once. I don't know how to do these things right. Here it is. Yeah, it's like falling into this grid. So this is a pictorial representation of some very beautiful mathematical stuff, but just to give you an idea. And the general theory of relativity makes this amazing prediction about time. So we are back to time now. So Einstein's theory implies that the flow of time is different for two observers in a gravitational field. So special relativity taught us that if you move with respect to each other, the notion of time has to be re-examined and changed. Einstein's theory tells you that in a gravitational field also, this is what happens. You see the clock on the top floor is moving much faster than on the bottom floor, right? Now this is it's a prediction of Einstein's theory. The equations tell you this is true, and this has been experimentally verified also. And it is this effect about the fact that time flows faster as you go away from gravitating objects is taken into account when, in the accuracy of the GPS systems that you use. There's a special relativity correction also because the satellite is moving very fast. And we saw previously that that will slow down. So you've got to compensate these, and this is a sort of a beautiful application of general relativity. And this is another one, actually, that the flow of time in the presence of a massive star or a black hole. I mean, see, you're far away from a gravitating object, time is going very reasonably, it slows down as you come near. And if you come near the horizon of a black hole, the black holes are these amazing objects, which have, which divide space-time into two parts. So the horizon, it's like a one-way street, classically, that you fall in and you cannot come out. Even if light falls in, it doesn't come out. So it's called a black hole for that reason. So the general theory of relativity has therefore changed our notion of time also. And it has also a practical application, which we use all the time today, actually, in our GPS systems. Okay, so now, I think I went too fast, looks like, because of you. So there can be questions then. Yeah, okay. I thought that it's very important for me to talk about the measurement of time and timepieces, just briefly, which are based on quantum mechanics, which is presently the theory of the real world. Sorry, I don't want to explain what quantum mechanics is, but the whole point is that classical physics sort of breaks down when you go to very short distances. So it cannot explain the stability of atoms, it cannot explain chemistry, it cannot explain nuclear physics, it cannot explain most things. So the mechanical clock that worked on the laws of classical mechanics was the standard timekeeper well into the 20th century. It was replaced by devices that work on quantum mechanics since maybe the middle or something of the 20th century. I'm not very clear about that, but so the quartz crystal is piezoelectric. You put pressure on it, it oscillates at a precise frequency. This frequency is exact, and this is used as a timekeeper in the quartz clock. Okay, but the most accurate timekeeper today is the so-called atomic clock. And why it is accurate and important, maybe I should explain that a little bit. It is not influenced by temperature or gravity or anything, actually. So you see, for example, clocks like pendulum clocks or even Harrison's clock or something, you cannot put on a satellite because up there the gravity is very, very weak. So the timekeeper in the satellite is an atomic clock. It's extremely robust to thermal fluctuations, to humidity. There's no humidity, and there's no gravity, more or less. So just the second is the duration. I mean, this is the definition of So let me explain to you what this is actually. So the cesium atom, I have some time, right? The cesium atom essentially has cesium-133 is a very stable system to work with, and what is important is that its lowest energy level is split by what is called hyperfine splitting. I mean, that's a very technical thing. I mean, you need to understand some quantum electrodynamics for that. So the spin of the nucleus of cesium and the spin of the electron, they interact with each other and they split the level. And this level splitting is very stable actually. So, you know, it's a discovery that in nature, this is the element that has this. There are other elements also, some of them that have this property, and then you can use them as good timekeepers because of the split, when you sort of excite this atom by a laser light, you sort of, you know, put it in a higher state, and when it decays, you lock onto that frequency. This is the frequency as a measure of time. So this is how the atomic clocks work. Now, I've just explained to you about a single clock actually, and there are problems with this, so you need to have an array of these atoms, and you know, there's a big experimental, what should I say, ongoing experimental work of making all these things much more accurate so that they don't lose time. So this is the strontium-based atomic timekeeper, which gains and loses only 1 second in 40 billion years. Now I want to say something about the nuclear clock. This is important actually. So we first talked about the energy levels of atoms, no? Of this cesium-133 atom. Now, people have discovered, this is all very, very current work, okay? This paper appeared in Nature in last year about nuclear clocks. So you now focus on the fine energy levels of thorium-229. And this clock, this energy level difference is much more stable to external perturbations, like thermal perturbations, which can affect an atom. Because this is it's a fine energy level difference of the nucleus actually. And it promises to be, it's not yet, the complete work is not yet done, 100 times more accurate and more robust to thermal noise than the previous best effort. And the previous best effort is the strontium one. So I think the point I want to make in this thing is that this sort of a accurate clock would be very sensitive to, for example, the presence of dark matter. Let me explain that. So when you calculate the hyperfine structure of a nuclear level, you are using standard laws of quantum electrodynamics, nuclear physics, and all that, and the standard model of particle physics. Now there is this elusive dark matter, you know, which which is a good part of the energy budget of the universe. And if this dark energy, this dark matter is an elementary particle, it will certainly have an interaction with the quarks, which make up the protons and the nucleons of this thorium nucleus. So the standard model prediction, which can be up to very high accuracy of this energy level difference, experimentally you may detect that it is not correct. And if it is not correct, then it may be, it's a hypothesis, due to the interactions of dark matter. So I thought that this is an amazing way of discovering dark matter, which has been so elusive up till now, in a laboratory experiment rather than an accelerator, which is much more expensive to make. And I think this is a very great idea, and it it basically underlies the fact that all time measuring devices obey the laws of physics, and hence their deviations can be inferred by sensitive timekeeping devices. So my last slide, oh, I'm sorry. I think in 5 minutes I can finish. Don't worry. The last slide is something which, you talk about time, but you don't talk about irreversibility, and which is so ubiquitous in our universe. So until now, we have discussed the emergence of the concept of time and its measurement in terms of regularities observed in nature, the motion of the earth, the passage of constellations, water clocks, mechanical quartz and cesium standard, all that we discussed. However, most phenomena in the real world exhibit a fundamental irreversibility. Consider the burning of a piece of wood. The final state is simply ash and carbon dioxide and other gases. One never observes the reversal of this, the final state assembling itself back into a piece of wood. Right? It's quite amazing, no, that our world is built like that. So this is a very important question which was approached in the 19th century, by Clausius, and then also so from the thermodynamic point of view, this is Clausius' introduction of the idea of entropy. One would explain this by saying that the entropy of the final state is greater than the initial state of the wood, and hence, by the empirical second law of thermodynamics, time reverse process does not happen. It's just a statement. There's no sort of deeper understanding. So to quantitatively understand this phenomena, Ludwig Boltzmann introduced a formula for the entropy of a gas as a measure of the number of internal states that make up the system, and showed under reasonable hypotheses of randomness, of collisions, that the entropy always increases in time. This is what is called Boltzmann's H theorem. And this led to the foundations of statistical physics. Of course, there is, of course, contribution by Maxwell here, and also by Gibbs. But I didn't want to get into all those details. After all, it's one slide, I'm allowed. It was subsequently adopted in quantum mechanics by von Neumann, and Claude Shannon gave a discrete version of Boltzmann's formula that forms the foundation of information communications theory. Notice this is 1932. This is 1948. Okay. Usually people don't know much about von Neumann's contribution. But, engineers use Shannon's theory, but in a sense is very much connected to this. And I do remember reading a story somewhere that John von Neumann told Shannon was at the Institute for Advanced Studies, to call it entropy, because then people will, take it more seriously or something like that. Okay, so this is the almost the last slide. And then I have not told you many things in this talk. I have not explained to you why the universe, our present universe, is experimentally in terms of data and observations, approximately 13.8 billion years old. I haven't told you about that time sequence. I haven't told you about the timelines of planet Earth, the whole science of carbon dating, etc. I haven't also told you about the origin of life and its timeline. These are all amazing things that have happened. So I haven't told you a good part about this amazing figure. This is a cartoon of our universe. We say there's some big bang due to some theorems of Hawking and Penrose. But we have absolutely no idea what happens here. And this is the sort of subject which this set of fellows called string theorists work on. We are interested in this part, and of course its implication at longer length scales. Okay, so this I didn't tell you anything about inflationary time or anything actually. So this just wanted to say this, and then I want to quote something which I'm very fond of. It's a quote from some exhibition I once saw in museum in Jerusalem, and it just struck me very deeply. So let me read it out. Most amazing is this realization that everything that exists in the universe came from a common origin. The material of your body and the material of my body are intrinsically related because they emerged from and are caught up in a single energetic event. Our ancestry stretches back through the life forms and into the stars, back to the beginnings of the universe. So most of this time sequences I actually didn't have any time to talk about, but I thought I should talk about this. And all this is new. None of the great figures of human history were aware of this. We are the first generation to live with an empirical view of the origin of the universe. We are the first humans to look into the night sky and see the birth of stars, the birth of galaxies, the birth of the cosmos as a whole, through our instruments. Our future as a species will be forged within this new story of the world. And I wanted to end this talk with the following. Since it's a science talk, so it's something we have to internalize from being a scientist and the application of the scientific method. So here we are, 13.8 billion years, this vast cooled down universe on a small rock called Earth. This is due to Feynman, a small rock of age 4 billion years, sailing through the universe as part of our galaxy, the Milky Way, with 100 billion other galaxies. This immensity and complexity must make us feel humble. And there is so much to be said about the perturbation of the state of the Earth by us, and about the preservation of our species and the others that we coexist with. I mean, this is a central challenge of our times. And I just wanted to say that maybe one way of addressing this challenge is by the use of the scientific method. So one of the most important developments of the last millennium is the scientific method as a means to access the idea of truth. What is the truth and how do you access it? And hopefully you will imbibe this and see the world in all its aspects, including our history, our sociology, our environment, and our survival as a planet through the lens of the scientific method. Cut off. Right, so thank you very much for being here with us. And thanks to the Nehru Planetarium for hosting Kaapi and Kuriosity. The ICTS outreach team for the extraordinary job they do. Web resources for images, one for use of his images, and Rugnayagam and Mandal for pointing to two amazing books that helped prepare this talk. Thank you very much. You saw one more slide. No. I blotted it out. Yeah, it is there, but it's a hidden slide. Okay.
So we'll take questions now. You can please raise your hands and I'll pass the mic to you. You can ask your questions.
Thank you for the talk. This question is regarding the use of atomic clock to measure dark matter. So since dark matter doesn't interact with periodic matter, so how does the process go about?
Yes, so it's possible. This is a theory. It's one possibility that dark matter does have very, very weak interactions with what we call matter that we describe in the standard model. So there will be those interactions, and if you take those into account, you may find a difference in this energy split, and that can be detected by this type of clock. That's what I wanted to say. I mean, so this is all written in this paper actually on nuclear clocks, which appeared last year. Nature.
Sir, I have a question regarding the second postulate of special relativity. Like
it says speed of light is constant in all inertial frames of references. This word inertial, it just pops up everywhere. So my question is speed of light also constant in non-inertial frames of references as well?
So inertial, by inertial frames, we basically mean frames which move at constant velocity with respect to each other. Okay? Now, if you want to extend that to frames which are not moving at constant velocity or accelerating with respect to each other, if you want to answer that question, you arrive at the general theory of relativity. That is the problem Einstein solved.
Like, have we measured different speeds in non-inertial frames?
No, so the idea of inertial flame, so suppose you take a sphere, okay, just as an example of a curved space. Yeah, Einstein's theory of general relativity says that space-time is, curved in the sense that it's described by a certain geometry. And let's assume for our explanation here that that geometry is a sphere. Now, if you take a sphere, it's a curved thing, right? But if you look at the sphere in a small little area on the sphere, it'll appear flat, right? So in general relativity also, if you take a point and look in a very small neighborhood, you will essentially find the laws of special relativity are valid. But if you go away from it, then you have to do it differently. That's
Oh, so special relativity doesn't work in accelerating frames? is it?
No, of course not. It does not actually.
Okay.
Certainly. It only works in the small area regions.
So we talked quite a lot on the clocks. Can you explain why they show clocks rotating clockwise?
I think that's a convention.
Why not anti-clockwise?
I mean, if all of us do anti-clockwise, one wouldn't find a difference, I think. Right?
Any other questions?
Yeah, it is challenged. Of course, it's challenged in the sense that Einstein's relativity theory does not work at very, 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 very short distances. It breaks down. It breaks down in the sense that we do not know. The problem is is how to combine Einstein's general theory of relativity with quantum mechanics. So if you are looking at space-time or events in the universe at very, very, very short distances, for example, during the Big Bang, seconds, 10 to the minus 40 seconds or something, then Einstein's general theory of relativity definitely breaks down. And so this is one of the outstanding problems of physics, how to reconcile these two theories of nature, which are very well experimentally tested in their own domains of applicability. So we are able to make sense of all astronomical observations on the basis of the general theory of relativity. We are able to make sense of all of atomic physics, molecular physics, nuclear physics, particle physics, up to distances of 10 to the minus 20 or more, less meters, 10 to the minus 18 meters, I think, which is the length scale that is accessible at the Large Hadron Collider in CERN. Quantum mechanics is good theory. But putting these together is problematic, and this problem was detected several decades ago and led to the development of a subject called string theory, which tries to sort of give a certain solution to this problem. But let me put it this way, that up till now we have been able to solve this problem only in toy models. In toy models means in models which we construct of gravity and particle physics, but which are not the realistic models actually. So we are not there quite. Yeah, but this is an important question. There's somebody there. Actually. Yeah. Yeah, please. Yes.
So my question is related to Maxwell. You referred about that light will appear to be the same. See, whether you move towards or away from the
Yeah.
light source. Right?
Yeah.
My question is related to this. Suppose if v is very small, then probably it's approximation, and we will feel the same thing. But suppose v is like c/2,
Yes.
something like that,
Yes.
and something is moving away from the light source.
Same.
What would be same?
Same answer.
So
Irrespective.
he will feel the right velocity is still
Same
c?
answer. Same answer.
Okay. What about he is accelerating, not with a constant velocity? He's also accelerating and trying to achieve to make up to.
That's a different question, actually.
So my question again, something related to is like why the actual acceleration is force, right? When there is an acceleration, constant velocity doesn't mean there is a force. But if there is an acceleration, means there is a force, some force is there. Why that affects light's velocity of perception of person? Is it the perception of the person which feels the light velocity is the same?
No, I think it's independent of person. It's just I can measure these things. But one point is that firstly, this assertion that the speed of light is the same for a person running towards or away from light is essentially an implication of a symmetry of the Maxwell's equations. So Maxwell's equations are there for electric and magnetic fields. Now, there's a certain symmetry. This Lorentz transformations of special relativity leave Maxwell's equations invariant, means they are the same for all movers. And this is the reason why the speed of light actually is the same for all inertial frames.
We are talking, when we say speed of light, are we talking about the mechanically observed speed or the perception of that?
Observed. You can observe speed of light by instruments, certainly, yeah.
Okay.
Not perception.
Okay. One more question related to the time and the distance. You said there is if somebody goes 100 meter above and there is 10 to the power 15 in tune of that, 1 by 10 to the 15th differences of the time. My question is again, is it the observation based on instruments or is it the observation based on perception? Would I be able to perceive? Because my perception also differs.
Of course, you will not be able to perceive, but you will invent instruments which will measure this.
Right, but when I go too far, right, my perception also changes, because when I am on near gravitation, my brain chemicals and all, they are affected by that, and that actually makes me to think or have my perception of time, right? So also I feel that time is passing, but instrument may measure differently.
But let me put it this way, that let's take the example of the GPS. Okay. So there is a satellite, 20,000 plus miles of orbiting the Earth. And there is a clock on that satellite. That's the atomic clock is there. Now this atomic clock actually moves faster because of general theory of relativity effects. But there is a slowing down of those time intervals because of special relativity. If you take all this into account, these corrections, then you are able to predict where you are located with high accuracy on Earth. So this is not just perception. This is, instruments are able to do these things, measure these things. There's one important point I always want to stress, that the ideas of the Einstein theory, they're very revolutionary. But from those ideas actually to the cell phone and its utility for global positioning systems is a big engineering challenge, which we should all appreciate. It took almost, I don't know how many years actually, maybe almost a century to do that.
Sir, hello. Sir, how should we approach the notion of negative time?
What do you mean by that?
Like it's counterintuitive, right? The idea that time, I mean, much like probability, like you have negative probability. So how do we?
Well, but when I write down Newton's laws, time is a real number. It can be positive, it can be negative. And then, of course, the issue is about the symmetry of the laws of nature under time reversal. That's a scientific question you can ask. And that symmetry was violated in elementary particle physics, discovered by Li and Yang, Madame Wu experiment. The electroweak interaction violates that symmetry. But the laws of nature, as they are symmetric with this breaking. I think you had a question. Sorry, just 1 minute. Particles what? Oh, I see. Oh, okay. So perhaps it's the same thing I was referring to, that in certain decays involving weak interactions, Li and Yang, who basically predicted theoretically that there will be a violation of this symmetry, which was experimentally then confirmed a bit later by Madame C.S. Wu. Is that something you're talking about? So the time reversal symmetry is violated there, actually.
We have this Feynman equations also where we talk about the arrow of time, right? And then then they talk about in some experiment that it moved in the reverse direction.
Okay. So there are many things. There are symmetries of the fundamental laws of nature, which perhaps I was responding to in the beginning. But then what happens when there's a large assembly of particles, or different species of particles interacting, like chemical reactions, or even stuff. What happens there is something which I alluded to. How do you explain from reversible laws at a very basic level, irreversibility, which we see in nature all around us, is a very important scientific question. And I think proof of these things mathematical proofs are very difficult. Very simple systems, one has been able to show that. But I think it's generally true that what Boltzmann said happens, that entropy increases always. Yeah. Is that, does it answer your question?
Perhaps not fully. So from that experiment, I kind of understood that some particle collision or whatever through the Large Hadron Collision, some particle actually moved back in time. That was my understanding of the article. Perhaps I understood it wrongly.
Why? Feynman? Oh, I see. So, I mean, they also move forward in time, but there's a description of this due to Richard Feynman as, antiparticles sort of moving backward in time. So that's a description, but antiparticle, that's a description actually. That's what I'm saying actually. So antiparticles are real particles. They have been observed. And their description, according to Feynman, originally was in terms of particles that go back in time. So, yeah, I understand the question, but the answer is that antiparticles are real particles, given mass, and they behave like just an electron. Positron behaves like an electron as a particle. There's other properties which, the positive charge, which sort of doesn't allow it to exist in a free state. Yeah.
Sir,
Yeah.
good afternoon, sir. Thank you for the wonderful talk. My question is based on your talk and this person's question. It's about the future of clocks, because from what I could understand, historically, clocks have been used to quantify intangible forces like gravity. That, like, mechanical clocks, they quantify gravitational force, which is intangible.
Intangible. Okay, I'm the
You cannot
mechanical-
see it, you cannot feel it,
I can feel it. I can, if I fall, I hurt myself.
but you need gravitational waves are not felt by ordinary people. So
No, no,
practically intangible
Okay, okay. Go
for
ahead.
normal people.
Go ahead, go ahead.
Okay. And utility for common people, because farmers use mechanical clocks. Fishermen can use mariners' clocks to find longitudes. Atomic clocks, as of today, it's mostly used by communication engineers and navigational engineers. Do you think we should go towards quantum clocks, or we should explore, materials being formed at, Earth's core to develop clocks in the future?
Yeah. I mean, this is ongoing research, actually. I mean, of a very important type. I mean, to develop more accurate optical clocks, which are atomic clocks, but with lots of the large array of atoms, and also the nuclear clock, which I mentioned about. Certainly, this is a very important experimental activity. In India, I don't know whether we are invested in this, but this is certainly a very important thing.
One small follow-up question. Do you think quantum clocks could decrease the irrelevance of this subject of study? Because if they get it wrong, then the utility for common people will come down. And
this quantum clock that I'm talking about actually is not for daily life, because the accuracy with which the time is being measured has implications elsewhere. We are okay with this simple mechanical watch in our lives. No problem.
Sir, so I'm not a physics student, but my question is based on how they visualize like general relativity in videos and all, where they put a ball in trampoline and then.
Yeah.
So what I was thinking is like, is the effect of gravity instantaneous, which you mentioned it is not, but like, does it act at full force at once? And second is like, if that is the case, like, how does it affect the Newton's law? So what I was thinking is like, let's say Newton's law give forces X. So does the object like kind of feels like zero gravity, then 1 up to X, or like how does it happen?
Okay, so I mean, the example, the pictorial way in which I try to explain general relativity was like a trampoline, right? So if you take a trampoline and you put a very heavy ball on it, it dips, right? Now you take a light ball, okay, and just throw it in the edge of the trampoline. What will it do? It'll fall towards the center. If you kick it very hard, it'll keep on circling, right? This is what Einstein's theory tells you as to what happens, that it's the curvature of space-time, that communicates to that ball how to move. And it is consistent with the speed of light being finite.
Oh, so what I was saying is like, will the curve will take some time to form? That means that effect of that curve will also take some time. Is that the case? Like if I look at a trampoline, let's say the trampoline was more stiff, or like, let's say it was bending over time. So like when I put a heavy object, it bends.
Certainly, I mean, for example, if you take two small black holes, for example, just, each of these black holes curves space in a certain way, and you collide them to make a bigger black hole. Then clearly, I mean, the space, the grid actually will shift and change, certainly. And at some point, it will sort of fall into some equilibrium, in which case you'll say this is the black hole and this is what it has. Effect of it on this very, very rigid grid. Yeah. Does that answer your question?
Yes. So like maybe a follow-up, which I don't want to answer in detail, but we still know that Newton's formula is correct for
speeds which are very small compared to the speed of light. Yes.
And what about mass? So we don't see any like, so for small objects or like for bigger objects also?
For any size objects, this is true actually. Yeah. I mean, the great thing about the laws of physics, the new laws you discover must contain the older ones.
So they should like verify the experiments.
In the tuning of some parameter. So Newtonian physics and special relativity, the parameter is the speed of light.
All right.
For classical physics and quantum mechanics, the parameter is what is called Planck's constant.
All right.
So it always has to be consistent.
Thank you.
Hello.
Yes. Yes.
Hello, sir. Maybe a slight deviation from the topic which you are covering, if you permit me. The speed of light, is it continuing to be at the maximal level or it has got a chance of breaching? Because I heard that some research was going on at MIT where they were trying to find some particles breaching this speed of light. And there was also some theoretical analysis at IISc Bangalore. There was long back. I recall the days of 75, 76, where there was a scientist here who theoretically evolved a particle and he named it also as tachyons, but it had no experimental backing. I mean, sorry, I don't know whether it related to your topic, but still as out of curiosity.
I think perhaps what you're asking is that how well have we experimentally verified this Lorentz invariant symmetry, which we use to do all our calculations. We are neglecting the gravitational field. Now, I think the Lorentz invariance has been verified experimentally. I mean, since the standard model works to 10 to the minus 18 centimeters, I would say that the Lorentz symmetry has been sort of verified to that short distance. Yes, I would say that. Regarding this tachyon that you talked about, so it's a particle which is supposed to go faster than the speed of light. But the point is that firstly, we never observed such objects. So maybe in some theories actually we can tolerate such things, but it's a bit too technical for me to tell you which theories you can tolerate that or not. So, yeah. Okay. Hi.
Yeah, so first question is just a follow-up on the very first question you got asked was about nuclear clocks and dark matter. So is it, I mean, you said it's an hypothesis. So is it just that dark matter, we know the interaction with the leptons per se is not, they don't interact with leptons, but they will interact with quarks or anything like that?
Yeah. So there is a what shall I say? There are models. These are hypotheses in which the dark matter is associated with an elementary particle. Actually, there are models like that. And in those models, this particle certainly interacts with the particles of the sand model. So if you are computing the energy, this very fine, hyperfine energy levels of this thorium nucleus, this is my understanding of it, okay? And if you find a deviation from a calculation which only used the standard model and standard nuclear physics, it would signal, it may signal the presence of dark matter. That's my understanding of it, actually. I mean, the popular articles talk about the constants of nature changing and all that. That's not right, really. What happens is that if you do a calculation of the energy level spectrum of this object, then clearly the additional interaction will create a certain energy level difference, which can be detected. Such a detection can, imply all hypotheses that there is dark matter. You have observed it on Earth. It's a very difficult problem to construct high energy accelerators. Actually, in the next 30 years, we will hopefully have such accelerators. Actually, but this is a terrestrial laboratory experiment in which you can do that.
Okay, another question was, I actually did not know how to formulate the question itself, but So our definition of time, perhaps like how we define a second, instead of the definition which we have in speed of light, if we just consider how we define a second in terms of cesium transitions, perhaps is it possible to get a more accurate definition of a second when you talk in terms of entropy and statistical mechanics? So perhaps the statistical probability will be able to give us more accuracy in the definition within certain limits compared to cesium atom.
I'm trying to figure out your question, what it means, but let me say the following, that are you saying that there may be some thermal noise in that clock, statistical thermal noise, which will make the measurement of time, which I mentioned about, it's, so many 9 point something gigahertz is the frequency. Will change that, and the answer to that is yes. This is the reason why people have stopped using single atoms, what are called ionic traps and all that, to do these experiments, but you have a whole array of them. So statistically, you can arrive at a very sharp and accurate answer. Is that what you were asking? Sorry, maybe.
No. It is actually pretty fine because whatever. So you said there could be some sort of problem. That's why we are not using one single atom.
Yeah, because experimentally I'm talking. I'm not talking in theory now.
Yeah.
The lab, right?
Yeah. So perhaps we can define time in terms of entropy change.
Yes.
Within something particular scenarios with particular parameters, well-defined parameters, and we can say perhaps that statistically 1 second could be in
so
terms
much
of
change of entropy.
Yeah.
Okay, I understand. You want to know the equation of motion for the entropy function, basically.
No,
So this is certainly something I understand in theory, but I don't know experimentally actually whether somebody is looking at this problem. Certainly, this is a well-defined problem because as I mentioned there, the entropy is defined in terms of this density matrix, which I talked about. This trace of rho log rho, this von Neumann formula for entropy. So the state of quantum mechanical systems depend on time, and that time dependence enters the formula for the entropy. So I can actually give you a formula for how that entropy will change in time. You have to be a little careful of this. In certain circumstances, it will never change. In certain other circumstances, it will change, but by how much, etc., we can calculate. But I don't know whether an experimentalist measures time by change of entropy. I don't know this. Sorry, I cannot answer this question.
No, thank you so much.
We'll take one last question.
Sir, I got a question related to Lorentz transformations. Like, if we have two inertial coordinate systems, if you know space and time coordinate of one, you can find the space and time coordinate of other with respect to other. So we know it's linear, right? Linear transformation. I mean, while doing the derivation of a Lorentz transformation, we assume that let x coordinate be some constant times x of other coordinate plus constant again.
Yeah, it's a linear
time. Yeah, again, time coordinate is equal to some. So my question is, why is x coordinate and t coordinate of this coordinate is depending on just x power 1 and t power 1 of this coordinate? Why did we not consider x square, x cube, x to power 5 and all? Why is it linear exactly?
Okay, that's because first answer to this question is that for most experiments and its associated theory, which is the Maxwell's theory, in sort of weak gravitational fields. This is the correct symmetry. Experiment tells you that. That is a linear transformation. Let me just always do it that way. I mean, so theory is invariant under these transformations, but it's experimentally also true, actually. Now, you are saying that I should consider, let's say, not linear, but higher powers. That's exactly what Einstein did in the general theory of relativity. Time and space are mixed up in a much more complicated way, non-linear way, actually. So that's the symmetry of the general theory of relativity. Certainly, yeah. That was one of the questions he was asking. Why is nature not invariant under these general symmetries? Why is it invariant only under the linear transformations?
So basically, it agrees with the experiments and we are very okay with it.
I'm okay with it. I mean, for experiments on planet Earth, terrestrial experiments, the linear transformation is fine. But if you want to conduct experiments, the large scale of the universe, then clearly it's different.
Okay, sir. Thank you.
Friends, we've covered a lot of ground in this talk, and we've had a lot of very good questions. And that signals the success of the event in some ways. We're trying to reach the public with the scientific world. And as a token of appreciation for Spenta's talk, I'd like Supurna to present him with a memento of this occasion.
Thank you. Thanks a lot.
Yeah. I would also like to thank all of you for coming. And I would also like to thank people for asking very searching questions that have made the event much more lively than we expected. We have not had such good questions from, a very enlightened audience, it looks like. And some of your questions are so searching that they probably at the edge of current knowledge. And that's precisely why we study physics and, pursue fundamental science. Yeah. So although we may not be able to satisfy your thirst for knowledge, we can satisfy your thirst for coffee. Please step outside and we can continue the discussion over there.